as we start into proving these trig identities in 5.2, we're going to start with algebra. Okay, so this does not use any of our trig identities. We're going to start with algebra. Prove the algebraic identity. So my job is to prove that the left equals the right. Okay, and our rule of thumb to do that is we take the left, we do whatever manipulations we can, legal manipulations, okay, legal mathematic manipulations, and then our goal is to get it to simplify and clean up to be 2. So what I usually do with these is I usually write out where I'm starting. So x squared minus 1 over x minus 1 minus x squared minus 1 over x plus 1. And we're going to do some things to that. Okay. And what I usually do then is I say, okay, equals 2. That's my goal. Okay. So I tend to write my goal down at the bottom. So I'm trying to get my left equal to my right. I'm not going to do anything with that 2. I just essentially want my answer to be 2. So that's part is you know the final answers on these. It's just how do we get there? Okay.
Do you
so
have do you have to number them, or can you just do work?
I just show my steps. I don't number my steps or anything fancy like that. I just show my steps.
Oh, so you don't have to do having the certain identity in there.
No, I don't list identities or anything.
Okay, so it's not.
I see what you're saying.
Proofs.
No, I do not.
You scared me there.
Now, you might see that pop up, I don't have any assigned, but you could see that, something like that pop up in a homework or a test question, those type of things. I don't usually, do that. I mean, we'll talk about what identity it is as we go through, because we're still going to be using things like Pythagorean identity, quotient identity, reciprocal identity, all those. So, but right now we got to think algebra for a moment just to get a feel for this. Thoughts of what I can do with that left? Could we do a common denominator? Okay. I can't add and subtract. Subtract them right now, can't I? So I can't subtract as is. If I'm going to subtract, I need a common denominator. Now, that is one good option. There's also another option here.
Multiply.
Say what?
Multiply these to cancel the 4 steps.
I don't think you could do that because they're squared.
You do the x minus 1 in parentheses, and then you have the x plus 1 in parentheses, and then you multiply. We did it a while ago.
So are you talking about factoring the numerators?
I don't think so. Yeah. But it's sure that seems promising.
Sounded like what she was talking about. Obviously.
Okay,
now, and here's what I'm going to say. 9 times out of 10, I'm going to go for let's get a common denominator. However, I see something in this one that will actually take us an easier route. And that is if I factor my numerators. What does x squared minus 1 factor into? X plus 1, x minus 1, difference of squares. So write this out. And here's the deal, guys. Don't skip all your steps and say, oh, I did those all in my head. I need to see steps written out, yes? Now, you guys know me. Sometimes I go overkill, and I write too many steps. But I need to see a decent amount of steps written out. So I'm going to write out my first fraction. Still has that denominator of x minus 1. And then x squared minus 1 factors into x plus 1 times x minus 1. Minus second fraction. The denominator is still x plus 1 in my numerator. X squared minus 1 factors into x plus 1, x minus 1. What do you notice in each fraction? They each have a factor that can cancel, yes? Okay. X minus 1 can cancel with x minus 1 in the first fraction. In the second fraction, x plus 1 can cancel with x plus 1. Now, what is my first numerator, or what's my first fraction now? Just x plus 1. Minus, what's my second one?
X minus.
And specifically, that x minus 1 is going to be subtracted, yes? Now what?
Like
Okay, so the way I have it written is it's x plus 1, and when we distribute that minus, it's going to be minus x and plus 1. And now we have x minus x, and 1 plus 1 is 2, I hope. Okay. Now, is that the only way we could have gone? No. Could we have gone the common denominator? We could have gone the common denominator. It just would have made it a little bit more difficult. Because we would have been adding an extra unnecessary factor in.
That's what I wanted to do, though. I just didn't know how to mention.
Yeah. So, okay. So that's always your job. Show your steps. Don't try and do a bunch of steps in your head. Show your steps. So, because here's the deal. You have to convince me, the grader, that you knew what you were doing and you didn't just happen to have the right step at the end. Okay? I have to feel convinced that, yes, they knew what they were doing. It wasn't just luck and they didn't just write down the final answer. Okay? Okay, let's try a trig identity now. This is going to be, this is more the name of our game today. Now, keep in mind, we've learned some identities to use, right? We got our Pythagorean identities, our quotient identities, the idea reciprocal identities, cofunction, even odd. We have the idea of being able to change everything to sine and cosine. We can combine fractions. We can split fractions. Those 5 suggestions we had for simplifying trig functions or trig expressions back in 5.1.1? Those 5 things all apply. Okay? So, my plan is, what am I starting with? Tan x plus cotangent x. So that's what I'm manipulating. That's what I'm working with. What am I trying to get to? Secant x cosecant. Yep. I knew it was supposed to be cosecant, but I don't know what it is. I struggle to write CSC for cosecant. Maybe because it's the only one that doesn't have a vowel as the second letter. But I always struggle.
It's probably some still there. It is on the TV.
Okay, guys. Thoughts on what we want to do to tangent plus cotangent. Here's the deal. We know the end result, but if that's confusing right now, don't even look at the end result right now. Just think, if this was back in lesson 5.1.1, and I had to work to clean this up, what is an option I would try?
Change this side to cosine. Yeah.
Okay.
Well, yeah.
Change everything to sine and cosines?
I like it.
It's what I would do. It's what comes to my brain. Again, I'm never going to say that's the only right option. So what do we know about tangent x?
Sin x
According to our quotient identities, it is sine x over cosine x. Plus, what do we know about cotangent x? Cosine x over sine x. Okay.
Oh, they don't cancel. I hate that.
They can't cancel because they're being added, not multiplied.
I never said that.
And then you need a common denominator.
Okay, so we have 2 fractions being added, different denominators, but we could get a common denominator. What would be my common denominator I'm going to get?
Cosine x, sin x.
Okay, cosine x, sine x, right? Because cosine and sine have nothing in common. So we're just going to multiply them together. Now, I'm going to go ahead and put that together as one fraction in my next step. If you want to leave it as 2 fractions for a moment, that's fine. Okay, first fraction has a denominator of cosine x. What is it missing?
Sin x.
So I'm going to multiply that one by sine x, and what I do to the denominator, we do to the top. What is sine x times sine x?
Sine x squared.
Sine squared x,
Yes.
okay? Plus, second fraction. has a denominator of sine x. What is it missing?
Cosine.
Cosine x. What I do to the denominator? We do to the numerator. What's cosine x times cosine x?
Sine squared x.
Cosine squared x.
Oh my gosh, this is kind of fun. Don't lie to yourself.
Still.
Okay. I have to veto the canceling of sines and cosines because on top there is a plus. You can't cancel parts of a sum or difference. We can cancel factors. If sine squared and cosine squared multiplied on top, I'd be all for it.
Sine squared or sine squared.
That equals 1.
Ah.
I told you it was fun.
That doesn't make it fun, Sophie.
Okay, so
It's like a puzzle.
sine squared x plus cosine squared x is one of our
Pythagorean.
Pythagorean identities, yes? I need to start. I have so many memes for Pythagorean identities, specifically this Pythagorean identity. I need to start putting some of those up for pre-calc now that you guys know them. I can't put them up for the algebra 2s, but. Okay, guys, so what do we know here?
1 over cosine.
Sine squared plus cosine squared is 1. And then the denominator is cosine x, sine x.
Which is equal to secant cosecant.
Is it? Because why?
Because
Secant and cosine.
I don't know, it's another identity.
Okay.
Oh, because of the
The quotient identity? No, that's not good. Reciprocal identity.
Reciprocal identities, right? A secant in the denominator, or excuse me, a cosine in the denominator has a reciprocal of secant. A sine in the denominator has a reciprocal of cosecant. You can leave it like this. You don't even necessarily have to go there's not really another step you have to go. If you're struggling with a visual, then you could take this step right here and you could break it up and think of it as 1 over cosine x times 1 over sine x. If you're struggling to see it, does that visual maybe help? And there you end up with your secant x, cosecant x.
I feel like I love so much.
Okay? And as you get into this, guys, you don't have to write what it's going to equal at the bottom. That's my teaching thing. But I'll be honest, when I'm doing these, I don't necessarily write ahead at the bottom, because I don't know how many spots it's going to take up. Okay, you ready for example 3? Actually, I shouldn't ask that because I think some of you are just working ahead on it. So.
Nope, I'm good.
No, it's just so.
I'm alright.
Okay,
Yeah, it's
But
just so.
it's just Sophie. It's just Sophie.
It's just so.
I saw several people writing.
Sophie's
So.
like, oh my gosh, it's a puzzle.
Okay.
Nobody likes puzzles, Sophie. Nobody likes
Just
puzzles.
physics, that's all it is. It's just putting little equations into other little equations and making a bigger equation.
Okay. I got my beginning and my end. Hannah suggesting common denominator.
I like it.
Because these denominators are conjugates, so same pieces, opposite signs in the middle, I definitely like that idea. So what's my common denominator going to look like? Okay, secant x minus 1 and secant x plus 1. Okay, I probably will FOIL these. Now remember, a lot of times I say I don't necessarily multiply the denominator out. But in this one, right, because it's a conjugate, I am going to because good stuff is going to happen there. Now, for the first step, though, I'm just going to write out that my common denominator is secant x minus 1 times secant x plus 1. If you wanted to go ahead and FOIL in that first step, I'm fine with that because I could definitely see that. If I was doing this on my own, I'd be willing to do that. But I'm teaching to a group, and so I don't do things quite the same as when I'm doing them on my own. Okay? Now, what is my first fraction missing? My first fraction is missing secant x plus 1. So we're going to multiply top and bottom by secant x plus 1. What is secant x plus 1 times 1?
Secant x plus 1.
Secant x plus 1. And then notice I'm going to go ahead and put these together as one fraction, right? Plus, because we're adding, what's my second fraction missing? Okay, I just should have left more room here. It is missing secant x minus 1. So I'm going to multiply top and bottom by secant x minus 1, yes?
Yes.
On top, what is 1 times secant x minus 1?
Secant x minus 1.
Secant x minus 1. Okay? If you didn't already, you probably should FOIL those conjugates, right? Secant x minus 1 times secant x plus 1 is going to be
Secant squared x minus 1.
secant squared x minus 1, because your middle plus secant x and minus secant x will cancel out. Okay, what about my numerator? What is secant x plus 1 plus secant x minus 1? No.
Secant x plus 2 secant x.
What is 1 secant x plus 1 secant x?
2 secant x.
2 secant x. And the 1 minus 1? Cancel.
0.
Okay. And this was right here. We did FOIL that denominator if you need to make a note to yourself. Okay.
Secant squared x minus 1 equals tangent squared x.
What are you guys seeing? There is a Pythagorean identity, yes? That same rule of you see squared trig functions, added or subtracted to other squared trig functions or ones, it's likely a Pythagorean identity. And so the Pythagorean identity in our notes is 1 plus tangent squared x equals secant squared x. I think that's the way it's written in our notes. And so right here, secant squared x minus 1, well, subtract the 1 over, yes. Tangent squared x equals secant squared x minus 1. So replace secant squared x minus 1 with tangent squared x. Now, that's another step I personally wouldn't do if I'm on my own. You're not going to see me writing this out on my own, off to the side. Now, does that mean you can't do it? No, definitely. Do this if you know, because sometimes it's hard to see. But when your secant squared x minus 1 magically becomes a tangent squared x, I'm going to expect that. So let's see. 2 secant x in the numerator, tangent squared x in our denominator. Thoughts on what to try next?
I'm thinking separate this fraction well.
Yeah.
What do you mean now?
Make 2 separate fractions.
Okay.
It's 2 over tan squared x and times it by secant x over tan squared x.
Oh.
So you can make it like easier.
Okay. Okay. So you said to do 2 over tan and then secant over tan. Okay. I see where you're going with that. I see it working. I'm not sure if everyone's going to see that one, though. I see it. I'm fine with it. It sounds legit. I think it'll work out just fine for you.
I didn't see that.
Did
Did not.
Did not.
Okay.
You guys were weird.
And what I'm toying with right now.
Okay, so
Okay, and here's the deal. I'm toying with, do I go that direction or do I go a different direction? Because here's the thing. If you see that one, you can make it work. But how do I teach
See,
if you're not going to see that one? Does that make sense?
I think I would have stopped there and asked Mario for help.
Okay.
Yeah, this is where I would probably.
But we need something to try. And as I said, I'm not opposed to Mario's idea, but
just get smarter.
okay. Think. Let's see. What did I do here? Because I know what I want to do.
I know, like, doing it as 1 over cosine. No, you can't do that because then you're just kind of taking a fraction. It's the secant out of there.
I see where they got the cotangent because tangent's in the denominator.
However,
It's off topic. That's
there's tangent squared, and we only need.
So maybe like the split
Cotangent.
wouldn't be a bad idea.
Okay. Now, so I could go Mario's idea. The other thing is, if you think back to our basic 5, okay, we have secant and tangent squared. We somehow need cotangent and cosecant to come out of that mess, right? What if in the interim, we change everything to sines and cosines and finagle them around? Does that make sense?
Yeah.
So in other words, if I take what I currently have, change it to sines and cosines, and then try and get what I need to get down here. Because this is where you do have to look at, okay, what is my end goal? We are going to have to look at that as we get closer to that spot. Now, if this is 2 secant divided by tangent squared, what do we know about secant?
That's 1 over cosine.
Okay, so, but the 2 is going to stay on top of that fraction, right? So can you agree that 2 secant is 2 over
Oh, that's kind of what I was saying.
cosine x? Can we agree to that? And then it's divided by tangent squared. Okay, so what is tangent squared x? Sine squared x over cosine squared x. But we're dividing by that, so we're going to keep change flip. So I'm going to say times cosine squared x over sine squared x. Are we okay with what I just did or no? All I did is technically change it to sines and cosines. That's the official step I took. That is right this time. I can do the cancel. So, yes, 1 cosine on bottom can cancel with 1 cosine on top. And now, okay, guys, you have to look. I have a 2, and I have a cosine on top. And I have a sine squared on bottom. This somehow has to magically become 2 cotangent cosecant. We have the 2, right? Manipulate here. What do we need to do with the cosine over sine squared to make it show this?
Separate them all out.
Separate them out. Because what is cotangent?
Cosine over sine.
That is cosine x over sine x.
Oh yeah, you just separate them out. Then you have a
What is cosecant?
1 over sine x.
1 over sine x. That 2 cosine over sine, 1 over sine. Does that legitimately come from 2 cosine x over sine squared x? Yeah, all the pieces are there. You see 2 cosine x over sine x, sine x. And then 2 cotangent cosecant. It checks. Okay? There are a lot of different ways we could go through that ending part of this. The beginning, I think you're going to get a common denominator. I think you're going to use that Pythagorean identity. But once you hit this point right here, it comes down to what do you see? Okay, I can only teach so much there. You just have to experiment with it. Okay, I'm going to go with you can start looking at the homework. But I will do at least one more example tomorrow. Maybe I'll do them both. I only have one down in my notes. Multiples of 3 if you start looking at the homework. What are multiples of 3?
3, 6, 9, 12, 15,
that it? Okay, I was just gonna ask, is it like every third
Okay.
one?
It's every third problem. All of the problem numbers you do should divide by 3. 3, 6, 9, 12, 15, 18, 21, 24, 27, 30, 33, 36, 39. Okay, bye.
Got it. I just